Ladies and gentlemen, in this presentation, I would like to demonstrate how we use modeling in order to link structural and functional information of the brain obtained non-invasively with a special focus on axonal transmission. Neural modeling is concerned with the mathematical description of neurons and neural populations in terms of functionality, and in particular with respect to the temporal evolution of membrane potentials and the generation of action potentials. And of course, with the transmission of action potentials between neurons. If you have several areas in the brain, then we have local circuitry, where we have quite short delays, which often can be absorbed into the cellular dynamics or descriptions of the cellular dynamics of the neurons. And we have longer delays between the areas that need to be accounted for explicitly. And of course, everything in between. So a single axon can be described by its transmission delay, which of course depends on the fiber length, which we can obtain non-invasively by diffusion MRI, for example, diffusion tractography, and by its transmission speed, which is again linked to microstructural properties, such as the diameter of the fiber, the relative thickness of the myelin sheath, quantified by the G ratio, and the parameters of the interruptions of the myelin sheath, the so-called nodes of Ranvier, and the distances, the internodal distances between these. So in order to establish this relationship, we have to model the axonal transmission, and there are very complicated, detailed numerical models around that do that job. However, they are really take into account many anatomical details, rely on a number of parameters which might not be accessible so easily, and because of their complexity, hamper real insight into parameter dependencies. So what we want to have is a simplified yet accurate analytical model. And that's what we build. This model depends on two components. First, we have a passive transmission part, which is simply the cable response to active channel currents, described by the cable equation, which is parameterized by the geometric and electric properties of the axon. And then we have the active part, the restoration of the action potential at the nodes of Ranvier, which we can describe using the Hodgkin-Huxley formalism. However, this involves the solution of a set of differential equations for every node, which is of course quite an overkill, because the response is actually stereotypic. Once the membrane potential has reached a certain threshold at the node of Ranvier, then this response is elicited. Therefore, it makes a lot of sense to use such a stereotypic response once computed from empirical data or from detailed models, and then use that again and again. How we do that explicitly in our context, please refer to the publication cited here. So how does this model work? First of all, it reproduces well-known experimental data from the literature. For example, the relationship between transmission velocity and fiber diameter is roughly linear in myelinated axons. Here we have the experimental range. And without further tweaking, our model gives something within that range if we assume reasonable values for the internode length, which is known to be a multiple of the fiber diameter and the G ratio. Similar results you can also obtain for unmyelinated fibers. If you look at the node and internode length, we get a relationship like this. We can observe that the velocity depends on the ratio between both, the optimum being at about 40, and of course the absolute value, the shorter the better. If we again reasonably assume that the internode length is about 100 times the diameter of the fiber, for example with 1 micron, then we can see that in a reasonable range of the node length from 1 to 2 microns, we only have a very little variability of velocity. So the influence of the node length is rather modest. But now the most interesting parameter, the myelin thickness or the G ratio. The G ratio dependence in turn depends on the diameter. The larger the diameter, the stronger the G ratio dependence, and the other way around, the larger the G ratio, that means the thinner the myelin, the less dependency we have on the diameter. This relationship roughly fits the well-known formula by Rushton, that the velocity is proportional to the product of the diameter and the square root of the logarithm of the inverse of the G ratio. There are slight deviations in our model, but qualitatively this fits quite well. So we have now a very simple, efficient, yet quite accurate model for single axons. And this we can use to effectively compute large number of axons or treat large number of axons, which is relevant because modeling single axons on neurons is quite limited because of several reasons. First of all, it's a computational power issue. So the networks become prohibitively large. Therefore, population models are often used like neural mass models. But also the information available, both functional, like EEG, MEG, or fMRI, and structural, like, for example, the G ratio or the diameter, are only available at the population level. And finally, population activity is also quite relevant for function in itself, in its own right. And for all these reasons, we do population modeling, and that involves modeling axon bundles rather than single axons. An axon bundle consists of many collinear axons with a distribution of diameters, where we have some empirical knowledge about. And what we now need to parameterize these axon bundles are distributions of all these parameters I have just mentioned: axon diameters, G ratio, node length, internode length, and so forth. Trivially, of course, one can just sum up all these axons and translate a distribution of all these, or distributions of all these parameters, to distributions of velocities. However, there's another phenomenon which we should consider, and that is the mutual influence between the different axons, the so-called apoptic coupling, which is mediated by extracellular potentials. If we have an action potential in one axon in a bundle with magnitudes of several tens of millivolts, then this causes extracellular potentials and in turn perturbation potentials in other axons. However, the magnitudes are quite small, so they're not quite likely to have a significant influence. On the other hand, early experiments in the 1940s have shown that apoptic coupling actually exists and can synchronize action potentials, slow transmission down, and even elicit action potentials in passive axons. However, the conditions were different. These were ex vivo experiments where the axons were few in number and embedded in highly resistive media. So how does the whole thing look in a more realistic setting? There we have to consider that an axon to be influenced is surrounded by not just one, but very many other axons potentially carrying action potentials. If we now assume that all these surrounding axons carry a perfectly synchronous spike, then these spikes will add up, the extracellular potentials will add up, and if we have a diameter more than 1 millimeter, we will have extracellular potentials in the order of several hundred millivolts, which have a spatial profile similar to an action potential. And this whole thing converges at diameters above a diameter of the fiber bundle of about 1 millimeter, so quite small. However, in reality, of course, these action potentials are not all synchronous. This is unrealistic. And we can imagine if they are more distributed along the axon, the adding up will reduce. Here we have simulated several cases where the action potentials, there's one action potential per axon, but they are distributed over a stretch of 2.5, 10, or even 50 millimeters. And especially this 50 millimeter case seems to be quite realistic, because if we assume realistic diameters from such a distribution here and the associated velocities, this corresponds to firing rates of 40 or 80 hertz, which is kind of something that would occur. So if we take this case as a realistic case and then see what happens to the transmission velocity, so or the transmission delay, then we can observe if we put into such an action potential a volley at the proximal end that has a certain duration, 1, 2, or 3 milliseconds, with one action potential within that period per axon, but not at every axon, but a certain percentage of the axons. This is the intensity, and we can see the higher the intensity, the more speed up we have, the larger the transmission velocity. Also, the narrower the input volley, that means the higher the synchronization of the input volley, the higher the speed up. And finally, the bundle diameter also, higher bundle diameter also makes faster action potential transmission. So we have a clear haptic coupling effect here that we would predict. So summarizing the whole thing, so haptic coupling is heterogeneous. Haptic coupling in heterogeneous fiber bundles accelerates action potential transmission, which increases with input intensity, input synchronization, and bundle diameter. Previous experimental and computational studies have found, however, a deceleration and a resynchronization due to haptic coupling. But we have to consider that in those studies that were computational, coupling among a small number of identical axons has been considered, and in the experiments, the axons were in addition isolated and embedded in highly resistive material. And that's the difference. And if we mimic these conditions in our simulations, we can also reproduce these results. So summarizing and concluding, what we do have is a simple and accurate model of action potential transmission through fiber bundles, which is determined most importantly by the G ratio and the axon diameter. These parameters we need individually, while other parameters like node length, for example, might be taken from the general literature. Axon bundles have properties beyond the sum of axons through haptic coupling, which depends on functional parameters, intensity, volley synchronization, and structural parameters. And these parameters, the G ratio, the axon diameter, and also the geometry of the axon bundle, this is what we ask our structural people, our MRI people, to gain information about from in vivo measurements. And finally, I would like to thank my collaborators, Helmut Schmidt, who did all these simulations, as well as Gerald Hahn and Gustavo Deco. Thank you very much.